Hey everybody, I wanted to go over one last type of problem in our approach here to electric potential and electric potential energy, and that is what's going on in a cathode ray tube. Now, a cathode ray tube, in a moment we'll go away to a clip, but basically what it is an electron gun. We take electrons that are boiled, if you will, or released from a metal out into the air, and we accelerate them through a potential. That gives them a velocity, therefore they have kinetic energy. Now the problem with the term accelerating potential is that it implies that one would solve the problem using forces and acceleration, when in fact that's not what we're going to do. Because the force would vary, just like for a rocket ship taking off from Earth, the force of gravity varies on it because the farther away that rocket ship gets, the force of gravity changes on it. The same is true for an electron that's going to be accelerating. So what do we do in that case? We can use conservation of energy. So before we get into the math, I'm going to go to that clip quickly and sort of show you close up what a cathode ray tube looks like. All right, so here's an old cathode ray tube with the cover taken off. It's actually an old oscilloscope. And what's really neat about this is it's still actually using vacuum tube technology. The things you see on the base of that platform there are actually vacuum tubes. Now looking at it from the top view there is the cathode ray tube. It's almost a perfect vacuum. Connected to the back are a bunch of different voltages and circuits. You can see here, this is actually a broken cathode ray tube. I inherited it broken. You can see the pins there that are the same as the pins you see on the cathode ray tube right there. Now, one of those is actually hooked up to a transformer that jacks the voltage up to nearly 1,000 volts. And these plates are actually connected to different points on the back end, and between each of those plates is a series of accelerating voltages. The two pieces at the end are actually deflection plates. All right, good, you're back. But we don't need to worry about that now. Here's what I'd like you to do. On a nice clean sheet of paper, can you draw a picture of that cathode ray tube? We're sort of be looking at this from a side view. It's a near vacuum inside. While you're drawing the picture, I'll tell you it's got a bit of a phosphorescent screen so that when the electrons strike that screen, they glow nice and green. The electrons, where do they come from? Well, they literally come from a hot wire. If you take a wire and you heat it up, you can heat it up with as little as 6 volts connected to a battery. And that hot wire will actually have electrons gain kinetic energy and jump off the end of the wire. When they do that, they're just sort of sitting there out in space, susceptible to electric fields. So what do? We place them between two large plates. And those plates, we often will hook up with an accelerating voltage. That's where the term comes from. Now, for a television, which is really the essential cathode ray tube of the 20th century, we would hook that up to a power supply that would reach 1,000 volts. And you say, 1,000 volts? I plug my TV, it goes into the outlet. Well, TVs have a transformer in them that transforms that 120 volts up to 1,000 or 2,000 volts. It's a reason why you should never take the back of your TV apart. It would hurt. Now, these plates with that large potential difference between them don't actually have electricity flowing from one place to the other because they're separated by air. But what they do have is an electric field. And I'm going to go ahead and draw in that electric field from the positive to the negative plates. And because it's an electron, that will cause the charge to accelerate. Which way? Yeah, that's right. To the right in the picture as I've drawn it. And it's going to go from here. Now, What they have is a charged plate, and believe it or not, it's got a hole in it. So that electron will accelerate towards the plate, and a lot of them will just hit the plate. But some of them will go right through. And we then have a beam of electrons traveling through space. We then can hook up a coil or magnets and change the direction of that path. And soon enough, you can get electrons that are traveling and hitting a screen to light up that phosphorescent pixel. And then you have that happen a million times a second and an image forms. But let's get to the math. So this cathode ray tube, this CRT, is really an electron gun. How about we look at some math? So I'm gonna redraw my, actually, you know what? I don't think you need to redraw the plates because I bet you did a pretty good job. Here's what I'd like to remind you of. The formulas we're going to deal with are electric potential energy, UE, would be Q times the voltage. Therefore, the change in electric potential energy would be Q times delta V. Nice. Now let me remind you from a previous problem we had done in class. The change in kinetic energy would be equal to the negative change in potential energy. Now, somebody asked a great question about this. Where the heck did negative sign come from? Well, turns out last year we kind of ignored it, but it was always there. If I take a mass and I drop it, if I take this mass and drop it, does it gain potential energy or lose potential? Stupid question, right? It obviously loses potential energy. It would be a negative change in potential. So our kinetic energy, which would be positive, our change in kinetic energy is positive. The negative signs over on this side would have to cancel out. I don't know if that's clear or not yet. Let's see how this plays out. Oh, I think I'm saved by the bell. Chill for a minute. Hopefully I edit this out too. We'll see if I remember to do it this time. All right, so we're back. Now, a couple things before we start getting into the math. I want to make sure in your diagram, did you clearly label that this ends up being an electron beam? If you didn't, go ahead and do that now. An electron beam is going to be traveling, so it's just one after the other. This hot wire, by the way, do you know what we call a hot wire? A cathode. Dun, dun, dun. That's why it's a cathode ray tube. Okay. Oh, yeah. That makes sense, doesn't it? Now, let's take a look at the math. I want to go ahead and find the change in kinetic energy. Now, that change in kinetic energy is going to be equal to the negative change in the potential energy. So sign-wise, let's take a look at it. I'm going to have a negative sign, Q delta V. Let's keep going. Now, the charge is going to be negative 1.6 times 10 to the negative 19 coulombs. It's negative because it's an electron. You guys know that. That's a piece of cake. Good. Now, my change in voltage, it went from 0 to 1,000. So 1,000 was the final voltage minus 0. And see what happens to those two negative signs? The change in kinetic energy gives me 1.6 times 10 to the minus 16 joules. Do you know what else it's equal to? What other unit of energy? It would also be equal to 1,000 electron volts, because the electron volt is, by definition, the amount of energy an electron has when it's accelerated across 1 volt. So if it was accelerated across 1,000 volts, how much energy? That's right, guys, 1,000. If you don't see that, which I'm not sure you do, it's going to be 1.6 times 10 to the negative 19 joules equals 1 electron volt. Just a reminder. Okay. All right. So we had a problem titled accelerating voltage or accelerating potential, and we did not use acceleration at all. Physics. What are you going to do? It's just the way it is. I'm going to do one last step here, which would be, what is the velocity of that, of the electrons in that beam? Okay? And then we'll call it. So what is the velocity of an electron in this case? Good. Some of you guys are already starting. That's awesome. So the change in kinetic energy is going to be 1/2 mv squared. Now, I'm assuming that it's starting at rest. All right. Now, my change in kinetic energy, I already have a value for that. So why don't I just take that and solve and get V all alone? So 2 times the change in kinetic energy divided by the mass equals the velocity. So 2 times, oh, we're using mass, which has kilograms in it. So I need to use energy, which has joules. And the mass of an electron, yep, some of you know it, but others, you can just look at the chart, right? You just look at the chart. It's 9.11 times 10 to the negative 31. And what I'd like you to do, get that calculator. I've got a velocity of 592,673.8977 meters per second. How's that look? Yeah, it looks stupid, doesn't it? Looks like that's written down by somebody who doesn't understand numbers. Given the information here and the precision we were working with, you don't know that velocity that close. Come on. So I'm going to round that to 5.9 times 10 to the 6. Oh, times 10 to the 5 meters per second. What do you think? I think you got this. I think you do. An accelerating voltage, a cathode ray tube, using conservation of energy to find the velocity of a fundamental particle. That's good stuff. Thanks, guys.